Assalamu alaikum. So in this video we are going to discuss our results for the multiplicity in proton-proton collision. So we are using the three energy dependence, the provided plots as you can see on the screen, and the provided plots basically shows the multiplicity distribution, okay, of the charge particle in proton-proton collision with having the center of mass energies at, you can see, this is for 0.9 tera electron volts. Similarly, this is for 7 tera electron volts, and this is for 13 tera electron volts. Okay, so let's first discuss the general shape of the distributions. Okay, so to discuss, as you can see, the distribution illustrates the probability. Here is the probability. In the y-axis is basically the distribution of the probability. Okay, and into the x-axis you can see the multiplicity distributions. Okay, so what is basically the multiplicity is, first of all you have to know that multiplicity is basically the total number of charged particles produced after the collision. So we are colliding proton and proton. So after the collision of pp, the amount of total charge produced is so called as the multiplicity, denoted by nch. Okay, and here on y-axis the distribution is the probability distribution. Okay, so as you can see, the distribution illustrates these distributions. Okay, these distributions illustrates the probability of finding a specific number of charged particles, okay, in the collision pp. Understood? Okay, as you can see, the curves features a peak. Here you can see peak of the graph is at the lower multiplicities. As you can see, this peak is at round about 10. Here is also like 12, and this peak is at like 20. Similarly, these peaks at lower multiplicity value, as you are going forward you can see there is an increase in multiplicity, but your peaks is at the lower multiplicity values. Here is also lower multiplicity value, and you can see here is the peak, and as you increasing, as you go forward to the multiplicity you can see there is no peak. So you can conclude that the curve features are peaks at the lower multiplicities. Understood? Followed by a rapid decay. Then you can see there is a rapid decay as there is an increase in the multiplicity. Understood? So what you can say that the lower multiplicity are more forward. Understood? The curve features a peak at lower multiplicity, then it extends to a rapid decrease. Now what it indicates? It basically indicates that the event with fewer number of particles are more frequent, because low multiplicity means fewer particles. Okay, so the results, first results, we conclude that at lower multiplicity you can say that the events with fewer particles are more frequent. Okay, means lower multiplicity particles are more frequent, means particles with low multiplicity are more frequent in these results, and particles with higher multiplicity are not so frequent. As you can see, there is a rapid decay in all these graphs, which having 0.9 energy, 0.70 ev or 13 ev. Understood? Okay, so also you can see as the energy increases, the peak shifted towards the higher multiplicity. Yes, you can see this is the lowest energy, and you can see there is a rapid decay. But as you increase the energy, you can see now this decay is little bit goes to shifted towards the higher multiplicity. Okay, you can see this decay here, this here, this here. But as you can see, this decays up to 150, and you can see as you increase the energy, this decays rapid decay and up to 20. So as you can increasing the energy, your peaks shifted towards the higher multiplicity. what you conclude that when you increase the amount of energy, you can produce high multiplicity particles. Okay, means more particles are then frequent, even not frequent, but you can say now you can check the high multiplicity particles. Okay, but the low multiplicity particles are more frequent in all these results. Okay, but you increase the energy, you can see that the peak shifted towards the higher multiplicity, and it suggests that higher average particle production now. So if you want higher particle production, you must have to increase the amount of energy. And you can see at the max energy of pp, and that is 13 TeV, you can see the peak shifted towards the higher multiplicity and up to 200, and also after 200 they should be go. Okay, and you can see that here high average particles produced, but here low particles produced. So by increasing the amount of energy, you can easily produce the higher average particle production. Okay. Let's again just another view to discuss the our multiplicity results with the variation of energies. Okay. So you can see as we are taking three energies, the minimum energy and that is 0.9 TeV, the middle energy and that is 70 eV, and the max energy of the proton-proton yet achieved we are using 13 TeV, and we have to check our results by variation with the energies. So as you can see, the distribution tail extends further for the higher energies. As you can go increasing energy, you can see details of these peaks. Details grow, goes broader and extends towards the higher energies. You can see here peaks at low, but as you increase the energy, you can see your peaks are now extended towards higher multiplicity. Again, you can see your peaks are extended towards the higher multiplicity. Probability is high now. You can see here low, and once you increase the energy, you can see it goes little bit above. Okay, and you can see it here at max 13 TeV, you can see the peaks are now more extended towards the higher multiplicity. Okay, so that high multiplicity events you can see become more likely as the collision energy increases. As I already told you, if you want high multiplicity, okay, events more likely to be found, you must have to increase energy. Okay, because at low energy, even at high energy, again I mentioned that although your low multiplicity particles are more frequent, you can see, but by increasing the amount of energy, somehow high multiplicity particles are some a bit more frequent, but not higher than the lower particle, but it's some extent towards higher multiplicity uh, compared to as low multiplicities. Understood? So this is the energy variation of the results of the multiplicity, and this trend indicates that higher collision energies allow for production of more particles due to increased available energy of the particle generator. Okay, so you can indicate from these results that higher collision energy, like in 13 tera electron volt, allows for the production of more particles. Because why? Because you can see in 13 tera electron volt, as the energy is max, and here is the higher multiplicity particles are produced. Okay, high multiplicity particles are frequent in this energy, so that it basically allows you more particle production. Okay, due to the increased available energy for the particle production. So that's basically the energy dependence in the results of multiplicity. Now let just move towards the comparison of data. Now check the jet dependence of our multiplicity results. So as you can see, we are visualizing our graphs at different energies, along with we are using setting our jet as jet on, represented by JD in our graphs, and when we set as 0 means our value of z is set as off, and j1 means when we set our jet value as 1, this is remains same for all the three different energies. Jet set is as on, off, and set as value 1, and we have to check the differences whenever we set as jet on, off, and 1. What happens to the multiplicity distribution of proton and proton? So as you can see across all the energies, JD, this is JD when your jet is set as on, black squares. These black curved squares represents the JD distribution when your jet is set as on. Okay, across all the energies, JD constantly shows a broader distribution. As you can see, JD has a broader distribution compared to blue and this red. Along here also, your black distribution means JD distribution are again broader compared to this blue and this. Okay, you can see again here the black distribution, JD distribution is more broader along between compared to this blue and this. Okay, so what it indicate basically higher particle production. Okay, means higher particle production when you set as jet on, because you can see it is broader curve, goes towards higher multiplicity. Higher multiplicity means more particle production. So if more particle production, so you can say the value when you set as JD on means your jet is on, you can see it goes to broader distribution. Broader values means goes to higher multiplicity, means higher particle production when you set your jet is as on. Understood? As compared to J1 and J0. J1 shows the intermediate behavior. As you can see, uh, when your jet is set as 1, it shows intermediate behavior. This is less broader than this black curve, and this is same in the case of 70 EVL energy, and this scenario is same for 13 tera electron volts. Means JD is greater than J1, then is greater than J0, and J0 shows a very low distribution. Okay, so that's basically the jet dependence. Okay, the you can also say that the J0 data set basically the peak at the lower multiplicity. You can see the peak of J0 is at the lower multiplicity. Understood? Also here, this red curve shows when your jet is set as off, and when your jet is off, your data set shows a peak at lower multiplicity. What it suggests that it represents event with lower particle activity. Here, lower multiplicity particles are more frequent. Understood? When your jet is set as 0, means when your jet is off, it shows lower multiplicity particles are more frequent. Understood? So that's the jet dependence in the case of multiplicity. Whereas your J1 lies between JD and J0, which displays the intermediate behavior. Okay, same as here, same as intermediate behavior, same as intermediate behavior here. This ordering remains the same for all the energies. JD is greater than J1 is greater than J0, okay? Reflecting different events of selecting criteria or physical processes influencing each data set. Understood? So that's basically the comparison of data and checking the jet dependence of multiplicity results in proton-proton collision. Okay, now, lastly, let's just discuss the implications for high energy physics of this multiplicity results in PP collisions. Okay, So the first implication is basically these results distribution provides insights into the particle physics. Definitely, we are using this in particle physics, and this provides insights into the particle production. As we know that the more particle produced, the high is the multiplicity is, because the multiplicity is the total number of particles produced. Okay, so this implications and this multiplicity distribution basically provides the insights into the particle production mechanism, okay, in proton-proton collision. And particularly, you can say that particularly how they changes by increasing the energies. Okay, as we checked our multiplicity by increasing the energies. Okay, so that's very crucial for the insights into the particle production mechanism in proton-proton collision, and particularly to know how about how they change by increasing the energies. Okay, the second implication of this multiplicity results in proton-proton collision is they serve as a test for theoretical model in quantum chromodynamics QCD, okay, which predicts the behavior of particle multiplicity at various energy scales. So in QCD, we must have to check the particles multiplicity behavior at different energies. So basically, this our results basically serve as a test of theoretical model, okay, framework for QCD quantum chromodynamics. So that's all for our results discussion of this multiplicity in proton-proton collision. In next lecture, we will discuss the pseudo-rapidity results in proton-proton collision for the same energies 0.9, then 7, and lastly the 13 tera electron volt. So till then, stay tuned with us. Take care. Allah Hafiz.